All right, so another thing we have to consider, like once we've kind of looked at the climate, we know we've got about 150 to 190 growing degree days, or 150 to 190 frost-free days rather, and we have the amount of growing degree days that we need in order to produce the wines that we want to produce. Um, we also need to consider elevation. It says altitude; it should really say elevation, of course, but um, so of course with elevation, you're going to have what's called the elevation lapse rate, or ELR, uh, where, say, like here on this diagram, at 1,000 meters, the average temperature is 23.5 degrees Celsius, and then we go up 1,000 and we lose about 6 degrees Celsius, right? In general, the elevation lapse rate is around 0.33 degrees Fahrenheit per 100-foot increase in elevation. But that's, of course, really variable. So, people often ask, what's the highest elevation I can plant a vineyard? And then I always say it just depends, which is a terrible answer, of course, but it's the truth, right? We don't know where the highest elevation is for a vineyard until we really know the elevation lapse rate in the area. So, for instance, in the Willamette Valley, we often say the highest you can go is about 800 or 900 feet. And also, that's not just due to it getting colder up there, but also simply you're getting more rainfall as you get higher, because the clouds are precipitating more at elevation. So you're getting more rainfall, more hail. But we do see vineyards at 1,000 feet or even above 1,000 feet in the Willamette Valley. But that is one thing you need to consider. And then, for instance, like in Bhutan, where I do a little bit of consulting, we've got vineyards at 4,000 to 6,000 feet, which is fine for that area. So for instance, here we see these are a couple of vineyards in the Chehalem Mountains AVA of the North Willamette Valley. So you can see this one here is Colleen Clemens on the, you can't see my cursor. There it goes. Colleen Clemens there at 570 feet in elevation. And they're getting about 1872 growing degree days at that site. It seems. This is information I pulled from the site Every Vine, which is sometimes accurate and sometimes not. But I mean, this is probably true, considering the wines they make at Colleen Clemens. They make some of the best Pinot Noir in the Willamette Valley, but they are definitely more, I hate to use the term, but on the Burgundian side of Pinot, a bit more acid, a bit lighter in style. And then, just 2 miles away as the crow flies, so very close to them, we go over the peak here, and this is kind of a big ridge line here. We go over the ridge, and at 1,200 feet, you see Laurel Vineyard, and they have, only 1,600 growing degree days, which is, again, these are in Fahrenheit. Growing degree days in Fahrenheit and Celsius are going to be different. But 1,600 growing degree days, which is not much. It's going to be very hard to get still Pinot Noir commercially ripe, what we'd consider commercially ripe, on that site. So maybe we could maybe be better for Chardonnay up here. Something that we, because we're with Chardonnay, for instance, we're only trying to get to about 21 bricks as opposed to still reds where we're trying to get maybe to 24, 25. Or potentially this would be good for, sparkling wine. Yeah. And then another thing we need to consider with regards to topography is not just elevation lapse rate, but also aspect of the vineyard. So in the northern hemisphere, the sun is going to be in the south, right? So the sun's around the equator. And then in the southern hemisphere, the sun is going to be in the north. So if we're in the northern hemisphere, we generally want our vineyards to be some sort of southerly aspect. And if we do that, those sites are going to be a little bit warmer, which is going to advance phenology. So south is going to have an advanced bud break. Also going to have more heating, more radiant heating of that fruit. And when the fruit heats up, that's also going to help you know, ripen it up quicker. So load more sugars faster. Also, it's going to degrade the acids a bit, so we're going to have less acid in that fruit potentially. And then also the heat's going to help degrade some negative aromas like methoxypyrazines that you get in Bordeaux reds, so the green aromas, but also helping accumulate other like positive varietal aromas like terpenes, thiols, those sorts of things. Also, of course, the maximum temperatures are going to be higher on the south-facing vineyards. So in general, in the northern hemisphere, we're shooting for something between southeast to southwest. Of course, southwest is going to be our warmest aspect because, of course, the hottest part of the day is when the sun is slightly in the west. At about around 1:30, 1:32 is usually when the hottest part of the day occurs. And then, of course, if we're east facing, it's going to be phenology is going to be hindered a little bit, brought back a little bit because it's really just getting that morning sun, and then we're losing sun as it goes over the hill in the west. West facing is going to be pretty advanced. Again, and that's just because in the west that's when we're getting a lot of sunlight hitting the vine also at the hottest part of the day. And then, of course, north facing. Again, this is all for the northern hemisphere. You'd reverse this chart for the southern hemisphere. But north facing is going to be quite cool. Phenology is going to be hindered by that and slowed down by that orientation. Heat load on the fruit's going to be less. So in some areas, north-facing slopes in the northern hemisphere may actually be useful. So for instance, in Walla Walla, Washington, it's very, very hot there. They grow a lot of Syrah, and Syrah can be kind of relatively prone to sunburn. So one way to avoid it is to just plant on a northern-facing slope. And it's so hot in Walla Walla that the north-facing slope actually doesn't really seem to have cause any issues in terms of fruit and wine quality. And in fact, some of the best vineyards in Walla Walla are on north-facing slopes because of that excessive heat. But then you can see, so I've taken data from the North Willamette Valley here, and I used it from every vine, and I was just trying to see how many vineyards were on south-facing aspects, so southeast to southwest, and it's about 75% of the vineyards in the North Willamette. So that really is the dominant aspect for vineyards because of this reason. So site selection and soil, oftentimes, so you'll hear people wax poetic about soil in the wine industry quite a lot, and in the marketing material and in the magazines. You'll often hear things like calcareous soils, deliver minerality to Chardonnay or something like this. We know that not to be true through science, and the reason people believe that, right, is they believe that soil is actually being conferred from the ground into the vascular tissue and then into the grape itself. So they actually think that minerals are moving from the soil into the grape. But a mineral particle is quite large and can't actually move through vascular tissue and be transported through the vine. The vine's taking up like ionic species and like really small molecules of things like nitrate, but not minerals. So that's kind of bogus. And you'll often hear these things like in the Willamette Valley, you'll hear winemakers say that like Jory soil, which is derived from volcanic material, confers like red fruit aroma, and then the Missoula floods confer some kind of maybe like brambly, wild, rustic tannins, whatever, and then the sedimentary soils will confer something else. So those kinds of things are anecdotal. They may kind of hold up, not necessarily because of the soil itself, but just because of like where the soils are located in the landscape, and their moisture regimes, but not really having to do with the bedrock itself. And for instance, we actually did do a tasting in the Willamette Valley of like Chardonnay, a really large tasting of Chardonnay grown on these different soils, and we really couldn't come to any conclusion as an industry as to what it was doing. It does make a great story, however. So I urge you to go ahead and use that in your marketing material as you move forward in your career, but it doesn't really hold up scientifically. So there really is no one best soil. There is no, soils aren't necessarily giving the vine something directly, like in the case of minerality. And soil parent material itself doesn't translate into wine quality. But what does have an impact is what I mentioned just earlier is soil moisture regime, and things so like soil texture and soil depth, and also like soil structure, and also how much organic matter is in that soil can impact the soil moisture regime, and that can have a big impact on wine quality. Like for instance, and we'll talk about water relations later, but for instance, one of the things we're trying to do for high quality wine production, especially for mini reds, is we're trying to limit water from fruit set until veraison in order to, essentially make smaller berries, get higher skin to juice ratios, but also by limiting water, putting it into stress, we can also increase the production of some positive secondary metabolites like some phenolics and some flavor precursors. So anything that impacts soil moisture regime, like texture, structure, and depth, and organic matter content, can have a big impact on potential wine quality and wine style. So like one of the things we're going to look at when we go and do site selection, of course, is the soil. It's one of the first things actually we do is just dig holes. And we're going to look at the physical features, which include texture. So that would be like clay, loam, sand, drainage, because we want to make sure that these soils are well drained. By the way, well drained does not mean dry. Well drained means simply that the water doesn't pond up in the soil very easily. But you can have like a deep soil with a high water holding capacity that's well drained. And then depth of soil as well, of course. The deeper a soil is, the more it's going to be able to hold water. And then, of course, the more depth of the soil, then potentially the less we're going to need to even irrigate over time. We're looking for things like rocks in the profiles. So rocky soils tend to hold less water, tend to drain quicker. Also we just simply want to know, is there a bunch of rocks that's going to cause problems for us from a operational perspective on the vineyard? Maybe we don't want to plant on super rocky soils because we want to be able to work the soil without destroying our equipment. And then also looking at things like bulk density of the soil, and that's important because that's a structural thing. So we want to know that the soil is less than 1.6 grams per cubic centimeter in density, at least for about 3 feet down, because roots can't penetrate beyond a bulk density of 1.6 grams per cubic centimeter. And if there may be some time like in the soil profile where there's what we call a hard pan, which is an area in the profile that's has a density beyond 1.6 grams per cubic centimeter. And in that instance, then we're going to need to rip it in order to fracture that pan up to get the roots through. Then we're also going to look at things like pH. Generally, soils are more acidic. So if they're more acidic, we might consider liming them to bring the pHs up and make more nutrients available. Sometimes soils can be alkaline. There are some soils in Napa that are what we call serpentine soils, and in those soils, they can be pHs above 8, and they actually need to be acidified. But however, we do try to avoid farming on those soils because it's difficult to acidify a soil, and it's pretty expensive. And then we'll look at things like macro and micronutrients. and potentially modify those through fertilization, either on the soil or on the plant itself. And then we'll even look for toxicity pans. So you can actually get these pans in the soil. The one we see most common is aluminum toxicity. And this isn't something we see a heck of a lot. I've seen it once in my career, but where I had a vineyard where I had a strange, like just bad growth. And I dug down into the soil. The roots weren't going that deep. They should have been, because it was a really rocky soil profile. No hard pan in the profile, but we did notice this weird colored pan or like area in the profile. And so what I did is I took soil samples down the profile, and then one of the samples that I took was in that weird colored pan, and then it was like a kind of a grayish color. And I sent that into the lab, and then we came back with a really high concentration of aluminum in that area of the soil profile. And that had to do with leaching, basically, in the profile. So yeah, texture is one thing we look at, which is the relative proportion of different sized particles. So remember from soil science, if you've taken it, the particle size, so gravel is not a soil particle, but this is just to show you something to sand, relative to sand. But it goes sand, silt, and clay being the smallest particle with the greatest surface area. So clay tends to hold more water because of that, and also tends to be like more fertile because it has great surface area, so it can hold on to more nutrients than sand or silts. And actually, what holds the most water is in the center of what we call the soil texture pyramid, or soil texture triangle. It's clay loam. So clay loam is this balance between silt, sand, and clays. The way this triangle works, by the way, is, so say you have 30% clay in a soil, and then you have 40% sand in the soil, right, leaving you with 30% silts in that soil. Now we have a clay loam right here, okay, in the center of that profile, or the center of the triangle, right? So soils that are going to have the highest water holding capacity are going to generally be these clay loams and the clays. And then as we go into the sands, of course, this is where we're going to have less water holding capacity because we have these larger particle size. There's less micropores. There's a bunch more macropores, and the water can just freely drain out of that soil, right? And then these soils, yeah, clay loams are going to typically be your most like nutrient-rich soils as well. And just to go over some key terms, because I'm going to just summarize some stuff quickly on a slide coming up. But field capacity refers to the amount of water that can be held in a soil after like excess water has been drained out, right? So if we saturate a soil so that the water's ponding on the surface, and then we just let it drain for like 24 hours, then we should be at about field capacity, because the water in what we call the macropores of the soil will have drained out, and then the water in the micropores will be held in by surface tension. And yeah, then that's the water that's actually technically available to the plant. So field capacity is like full water availability. And then permanent wilting point is the minimum amount of water in the soil that's required for the plant not to wilt. And we can use, by the way, I should mention what these are. So this is what's called a tensiometer. This is an old way of measuring soil water availability. And we can actually, what it does is you put water in this tube, and then there's a porous tip here at the bottom of the tensiometer. And then as the soil dries out, the water moves from area of high to low concentration. And then it pulls a vacuum here. And then you measure how much of a vacuum you're pulling on that gauge. And that's where we get these like kind of soil water potential measurements. So field capacity is when we're pulling negative 0.33 bars here. And then permanent wilting point is when we're pulling negative 15 bars. And really permanent wilting point is actually when the plant is wilting at midday. And then so water holding capacity is the amount of water the soil can hold between, it's really actually between field capacity and or it's actually just the total amount of field capacity rather, and then available water is actually the amount of water that a plant can take up, which is the amount between field capacity and permanent wilting point. So if you see these things as you're doing your project for this class, if you see these terms, that's what this all means. And really what you should be concerned about mostly is available water content in the soil and how much water you can actually hold. And cation exchange capacity, this is a kind of an index, basically. It has units, but it's essentially how chemically fertile or how potentially chemically fertile a soil is. So it's the total capacity of a soil to hold exchangeable cations. And the reason we talk about cations and not anions is because soil particles are largely like they're a net negative charge. So the cations actually adhere to the soil particle, and then you get cation exchange where the root actually puts out hydrogen protons, and then those cations displace cations on the soil particle in order to get them into the root. So like in this case, you see hydrogen displacing potassium, and then the root's taking up potassium. But yeah, so it's kind of a measure of how chemically fertile a soil is. So the higher the CEC, the higher fertility of that soil, how higher chemical fertility. So this is kind of the impact of texture broken down. So sands typically have low CECs because they have less surface area than the smaller particles. They have low field capacities because they have a lot of macropores. So the water just gets in and drains out rather than being held in to the micropores that are formed by clays. They will have high permanent wilting points. Again, because the water is just draining out quickly. You can't really hold much in there. And yeah, low water holding capacity, again, because of the macropores, the abundance thereof. And then low available water, again, because of macropores. And then the inverse is true for clays as we move into the finer textures of that of soil, right? So one thing we can do is look at soil maps. So those of you that have vineyards for your projects in the United States, it's going to be quite easy for you because you can go to the USDA Soil Web Survey and you can draw little polygons around your vineyards and then start finding information out about the dominant soil types on your property. And we really do have one of the best systems for soil maps here in the United States. There's a pretty good system for New Zealand, so you guys should have a good go at it. For the other groups, for like Chile and France, it's going to be a little bit harder to find good information on those soils. For France, I have some information that I'll give y'all, and for the Montpellier region. For Chile, it's going to be a bit of a struggle because they don't have a really great system for soil mapping there. But these soil maps can tell you things about texture and drainage and potential management issues, so those sorts of things. So like here we can see this is for Witzel series, which is actually from this farm here. This is in the North Willamette Valley, but you can see things like they describe each of the areas in the profile, and so this is for like diagnostics. So you can go through and see, do I actually have Witzel, and actually dig a hole and check it based off of this. You can see things like competing series. So these are series that are closely related to Witzel, which can help you diagnose, do you have Witzel or maybe you have something else. It also tells you geographic setting for that soil. So again, if you're not, so this says Witzel soils are gently to very steeply sloping hills and mountains between 200 to 2,200 feet. So, if we're on valley floor and we're at 100 feet, we probably don't have Witzel. So again, this is just kind of a way to diagnose if you actually have it. This tells you like the soil is formed in loamy colluvium derived from basalt with minor component of loess. So that means, loamy is soil texture, colluvium is material that's come down mountains and hillsides. And then basalt, of course, is like bedrock from lava flows. And then loess is windblown soil material. Yeah, it gives you some idea of the climate there. Then it'll talk about drainage and permeability here. It says it's well drained, moderately slow permeability. And again, that's probably because, so this is a loamy textured soil. So we have a lot of micropores. So it's not going to, water's not going to get in super quickly, but when it does get in, it's not going to pond up because it's well drained. Okay, so there's quite a lot you can gain from the USDA soil surveys. So again, we're looking for things like for drainage. So anything like hard pans are typically the most common impediments for drainage that we find. And these are formed through natural processes and also through human processes. So naturally, you just get pans over time because of weathering, and the smaller particles will move through the soil profile and be pushed down and then eventually form this area somewhere in the profile that is hard and dense. But then also we get it from plowing as well. So just excessive plowing, especially if people were using the old-fashioned moldboard plow over and over and over, then we'll get pans where that moldboard plow meets the subsoil. So that's often why we call these plow pans. And also things like traffic, of course, if you had equipment running over it over and over, you're going to cause pans. So those things we're going to want to rip. We can deal with these. We can rip them and fracture them to get the roots down. So this is how we do it. This is a subsoiler or a ripper. And generally we will rip soils actually using caterpillars, like D9 to D11 caterpillars, and with a shank or two. So generally it's not this. These are actually small shanks. But generally with a shank or two, that's about 3 to 5 feet deep, and really get deep in the soil and rip up the pans. We also use it to rip up big boulders and stuff as well, which can cause issues when we go to drive posts in the ground. Another thing we might consider is if the drainage is poor on that soil, we may consider putting in drain tile. And the way this works is we need to do it about it depends on the site and the soil texture. But generally we do it about every 14 to 21 feet. And we run this perforated tubing down the slope, and then it'll connect into what we call a header tile, and then it'll drain out into some sort of culvert, and this will help drain the soil out. So here in the Finger Lakes, there's basically drain tile in every single vineyard. And then another thing we have to consider when doing site selection is slope. So air drains down slopes, and of course the cold air is going to drain down the slope, and then it's going to pond in the low-lying area of a property. So in this situation here, if we look over on the left of this diagram, it might be that we want to plant the vineyard up on the slope, but not necessarily plant down here in the low-lying area, because it's going to get perennially frosted out. Or maybe we do want to plant down here, but we just want it to be a separate block that we can manage year in, year out, like differently. Maybe put in some fans or whatever to try to keep the frost off, or it's just. But we know if we plant down here, we're running a risk of increased frost. The other thing that can happen is if there's like a impediment to air movement. So like here we have a tree. So this would be like a tree line or like a forest here, a little forested patch. The air moves down, and then it just ponds up behind the impediment to air movement. So in this case, we'd want to remove the tree line, that little forest, in order to get that air to move down the slope to be just like this. Let's go back. So yeah, so that's one thing we want to consider, is potentially planting on slopes and areas that are frost prone to avoid air ponding up. Right, and then if we start thinking about soil and chemical fertility, pH is a big thing we need to consider when we're planting. The reason being because we're shooting for a pH of around 6 to 6.5, And here you can see it says 6.2 to 7.3. Just ignore that. We're really, for vinifera, we're shooting for this range. And the reason is nutrient availability. So this diagram here is a famous one. And where the nutrient is in green, that is the pH where it's at its most plant available state. So you can see if we go up like 6.5, molybdenum is like pretty available still, but they're all pretty available. Maybe iron is a little less, but still it's pretty good. They're all pretty much in the green, right? So that's kind of why it's this 6 to 6.5 range that we're shooting for. But then you can see look at phosphorus. With phosphorus, as we go down like below 6, it starts to become quickly unavailable, right? And that's because with phosphorus particularly, phosphorus forms these complexes, these insoluble complexes with like iron and aluminum at these lower pH values, and the vine can't take that up anymore. The good thing with phosphorus, though, is that if you are in soils with high organic matter content, you can end up kind of compensating for that low pH. So in Oregon, oftentimes we have pHs around 5, which, according to this diagram, would probably be pretty limiting for phosphorus. But we generally don't see phosphorus deficiencies at pH 5 in Oregon because we have 5%, 5-6% organic matter, giving us quite a bit of phosphorus. So you can compensate. But in general, we are trying to get our pHs up into this range so that we have all of our nutrients available. Right, and the way we do that is by using calcium carbonate or lime. And we apply the lime to the soil, and we're talking about tons per acre at a time. Generally, we do about 3 tons per acre in one go. And then we may do that year after year until we get sometimes, maybe 9, 12 tons per acre of lime on the soil, depending on how much we have to raise that soil pH. But the way it works is the lime reacts with the hydrogen protons in the soil. Remember, pH is just an inverse logarithm of the concentration of hydrogen protons. And so the calcium carbonate hits the soil. The water helps break it up into calcium ions, which bind on to the soil colloids, which are, again, net negative charge. And then it displaces hydrogen protons on the colloid, and then the hydrogen protons react with the carbonate, and they forms a little bit of CO2 and water, right? Thereby taking the hydrogen proton out of solution and then increasing pH because you have less hydrogen protons. Right, so the most common thing we see is low pH soils, which we correct through liming. And we can either use dolomite or calcitic lime. Dolomite has magnesium in it, so if you need to add magnesium as well, you could potentially use dolomite. Dolomite's quite a bit more expensive than calcitic lime, though. So another way to do it would just be to add a bunch of magnesium sulfate or Epsom salts when you do your calcitic lime application. And then calcitic lime is basically just completely calcium. It's best, we generally try to make the first application before we rip soil. And we generally rip vineyards, we rip soil before we plant. It's for many people, it's just kind of a matter of course when you're planting a vineyard, rightly or wrongly. But when we make a lime application, initially we're going to do probably about 3-4 tons per acre. And we're going to do it before we rip because we want to rip that lime down into the soil profile and get it deep. If we just put it on the top, it might not actually travel down into the soil profile. Another thing we're going to look at is in chemical fertility is macro and micronutrient concentrations. This is generally the ranges we're looking for when we do soil tests for vineyards. You can see nitrogen has no ideal concentration, and that's because it's really hard to actually accurately measure plant available nitrogen in soils, and that's because it changes over time. Nitrogen's not stable. Concentrations aren't stable because you get mineralization of organic matter, and then thereby getting releases of nitrogen. So when you have more water and it's warmer, then you're gonna have more mineralization of that organic matter and more nitrate. And then if it's like cool and dry, you're gonna have less. So as you can imagine, it's not very stable over time. One thing you should notice is if you go look around for ideal concentrations for nutrients, these are going to vary from university to university. They're not really truly set in stone. These are just kind of guidelines. I think this one may be from Virginia Tech. I actually can't remember. But you'll see slight differences when you look at like Virginia Tech or Oregon State. But no real like glaring differences. But yeah, most of these we can modify. Macronutrients, a lot of times we'll try to modify through, if they're deficient, we'll try to modify by putting on fertilizers. The micronutrients we generally will not try to modify with soil fertilizer. And that's because if we get it wrong, we could potentially easily go into a toxicity. We don't see toxicities with macronutrients, but we do see toxicities with micronutrients. So a lot of times if these micronutrients are deficient, then we will supplement with foliar sprays. All right, so the next step is we're going to talk about actually planning out a site.